vertical asymptotes and horizontal asymptotes is way more than that. So,
Actually, I do have a question.
yes, please.
So for the last one, number 7,
Yes.
we have to write that it's a polynomial. We have to write that it is continuous everywhere because it's a polynomial.
At least on the interval you found. But this polynomial, the polynomial functions are continuous everywhere. Right? But at least you have to write, if it's not a polynomial function, it could have natural log in it, it could have anything, right? A rational function. But if it's polynomial, it's continuous everywhere. But if it's anything else, you have to say that it's at least continuous on the interval you found, like on -1, 0.
Okay.
At least. It's part of the theorem. The theorem has 2 hypotheses. And please add to the list the squeeze theorem. Sorry, to the list of topics for Thursday, please. I think I forgot to mention that. My apologies. So please do not forget the squeeze theorem to add to the list. Thank you. So, like the squeeze theorem, which has 2 hypotheses. What are the 2 hypotheses of the squeeze theorem? That the function is squeezed. That's the first theorem. The function is squeezed. There is a function as a lower bound and there is a function as an upper bound. That's the first hypothesis. The second hypothesis is that these 2 limits exist and are the same. And only from these 2 conditions I can draw the conclusion that the limit of the middle one exists and is the same. Same thing with the intermediate value theorem. 2 hypotheses. The function has to be continuous on that interval. I don't care if it changes sign, but it's not continuous. It doesn't have to go through 0. It's a perfect question. Let me show. If we don't consider, if the function is not continuous, so this is A and this is B, and here's the situation. See, this function changes sign on AB. It's positive at A and it's negative at B. But if it's not continuous, there is no C for which f of C is 0. So it's a crucial part of the theorem. So that's why the function must be continuous. Either coming from below, from negative to positive, or coming from above, from positive to negative. But it must be continuous and it must change sign. Because if it's not continuous, the theorem is not applicable. I cannot draw a conclusion. It's a very good question. Thank you, Colin. Is that okay?
Okay.
Perfect. Yes.
And so you said f of c is equals 0 because it's positive?
No.
Oh.
Because the function is continuous and it changes sign between A and B.
So it's supposed to be 0.
F of c will be 0. Okay, the function is continuous. F of A is negative. F of B is positive. Therefore, there is a C because of these conditions. Therefore, there is a C such that f of c is 0 between A and B. Because if the function is not continuous, it changes sign. See, it's positive here and it's negative here, but it's not continuous. It doesn't cross the x-axis. It does not have a 0 or an x-intercept. Good. Anything else? Oh yeah, I wanted to work on problem 8. Other questions for me here? I lost track of my pages here. Okay, so we have f of x, which is x plus 1 over x squared plus 3x plus 2. I don't need parentheses around the denominator, by the way. It's not a mistake, but I don't need them. In my mind, I was already factoring the denominator this way. Okay. Good. So what type of function is this?
Rational.
Rational. So once I find a horizontal asymptote, then it will be the same. It's not going to be positive 3 at infinity and negative 3 at negative infinity or vice versa, right? The horizontal asymptote will be the same on both sides. So I don't have to really find both, or I can just write. Okay, what next? What should I do next? Yes, so then I have x plus 1 and the denominator is?
X plus 2, x plus 1.
Excellent. Good. So then, what happens next? Well, there are a few things that we have to deal with. So let's separate them. When I determine the limit as x approaches infinity, and it will be the same with x approaches negative infinity, I don't have to write it twice, of x plus 1 over x squared plus 3x plus 2. I'm going to write the title in a moment, right here, in a second. What am I trying to determine when I am calculating this limit? What am I trying to determine?
It's continuity.
The end behavior, right? When I'm trying to determine the limit at infinity or negative infinity, right? I'm looking far to negative infinity and far to positive infinity, right? I'm trying to find the end behavior of this function, right? Okay, how do we approach this? What do we need to do? What have we done in the past with something like this? So this is what is called end behavior. Of course, for such a function will be the horizontal asymptote, because it's a rational function. That's why I asked you from the very beginning. So this is a rational function. I'm trying to find the end behavior. For such a function, the end behavior is identical with what? The potential horizontal asymptote. Some of these graphs will have a, what is this called? Slant asymptote. Perfect. Okay. Not this one, however. So how do I approach this? This is very important. We went through step by step with this. What did we do? We looked at the numerator, and we said the numerator approaches
Positive.
excellent. We looked at the denominator approaches
Positive.
good. So we know it's an indeterminate case. And then I write limit as x approaches infinity. And what do I do? Without looking at the denominator, we identify the degree of the numerator, and we said the degree was. So factor it out for me, please. What do I write?
X.
And what is left in parentheses?
1.
Excellent. Now I'm looking at the denominator. You understand they are completely separate. I don't want you. Yes, there is a different method in the book. If you prefer that method, I'm fine. They multiply the top and the bottom, blah, blah, blah. I don't think it's necessary, but if you understand that method or anyone presents you that method and you understand and you're comfortable with it, please use it. Okay, the degree in the denominator, please.
2.
So what do I do? What do I factor out? Good. So please tell me what you have in parentheses.
1 plus whatever x plus 2 over x squared.
Thank you, Tara. Excellent. Good. So now, only because it approaches infinity, where does this go? Where does this go? Where does this go?
0.
All of them. Excellent. Thank you, Vicky. And now I simplify an x from the top and I have a 1. I simplify an x from the denominator and I get x. All this, without looking here, all this is going where?
It's going to be 1.
But I have 1 over x when x approaches infinity in front. So the answer is?
0.
Thank you very much. So y equals 0, horizontal asymptote. It's a rational function. The horizontal asymptote will be the same at both ends. There is no need to recalculate for x approaching negative infinity. Any questions? So this piece is done. We determined the end behavior, which is the same with the horizontal asymptote, 0. And now, what do you think the other side would be? Of course.
Vertical.
Of course. Vertical asymptotes. as well as, which is not the same thing. A hole in the graph does not mean a vertical asymptote. Okay, good, so let's take a look. Now I'm looking at the factored form. I will never look at the factored form when I determine the end behavior or horizontal asymptotes. I need this raw form. But now I'm done with that, so I'm going to look at the factored form. And I noticed something very important here. What do I notice?
You can cancel out x plus 1.
Excellent. Not before what? I cannot cancel anything before I do something. And then I can cancel.
Do you have to write it as a limit first?
No?
Right.
Exactly. If I don't write the domain, thank you, Paige. If I don't write the domain on the raw equation, after I simplify, the domain is different. So please be very careful. Give me the restrictions, please. What are the restrictions here?
-2 and then
Perfect. Now I can simplify. And the simplified form is 1 over x plus 2. However, this function has two different situations. One situation is when x minus 1, when x plus 1, in other words, the condition, the restriction x equals -1, becomes a hole in the graph. Why is this a hole in the graph? Because the factor goes away from the top and from the denominator. So this becomes a hole in the graph. Fine, but I still have to find the limits, left and right of the hole. This one stays in the final form. Because it stays in the final form, this will become a vertical asymptote. The factor that goes away is a hole in the graph because the function is still undefined at -1. Because this is not the function we're talking about. This is the function we're talking about. And this function is undefined at -1. So, two things here. Number one, for a hole, I have to find the limit as x approaches -1 from the left of 1 over x plus 2, and limit as x approaches -1 from the right of 1 over x plus 2, and you'll tell me what that is. And two, for the vertical asymptote, I have to determine the limit as x approaches -2 from the left of 1 over x plus 2, and limit as x approaches -2 from the right over 1 over x plus 2. Totally different situations. Why? Because this function has two restrictions. One factor that goes away, that creates a hole in the graph, and the other one that stays in the simplified form, which eventually turns into a vertical asymptote. When we get to chapter 3, when we graph these functions, you'll see what happens. Actually, it's chapter 4, sorry. Chapter 3 is just differentiation rules. In chapter 4, we apply differentiation rules to applications. Okay, so can anyone give us this limit? Careful, one more time.
That's just 1.
And the other one must be the same. It's a hole in the graph. So what is this one? 1. So what is the hole? Can anyone give us the ordered pair of the hole?
-1.
Excellent. Thank you, Cole. Good. So now here plug it in. Of course you're going to get a number over 0. And you know that there is no hope, as we expect. It's going to be a vertical asymptote. But please give me the limit of the first and the limit from the second. And we know that x equals -2 vertical asymptote. No question there. So it's 1 over 0. So I have to write either infinity or negative infinity, right? So negative 2 from the left, it's negative 2.1. What do I get?
Negative infinity.
And negative 2 from the right, like negative 1.9. Any questions? So this is something that we will need a lot when we graph functions in chapter 4. We need to determine the limits to know where the function is going for the whole, because there is a limit there. It's a removable discontinuity. And I'm going to do that right now on this function. So obviously, here's an example for you. So we had f of x equals x plus 1 over x squared plus 3x plus 2. At x equals negative 1, it has a removable discontinuity. Yes, it's discontinuous at negative 2 as well. But if I want to create a function that is continuous at negative 1, I will create the function g of x as x plus 1 over x squared plus 3x plus 2 for x anything but negative 1. And how will I define this function at negative 1 to make it continuous at negative 1?
Did you put it in negative form on it?
Because the limits from the left and the right are 1. If I want to fill in this gap, the hole, I have to put in 1. So I created a new function. It's guaranteed to be continuous at negative 1. Because the limit from the left and the limit from the right at negative 1 is 1. So I created a point that fills in that hole. What point? Negative 1, 1. Because the limits from left and right are both 1. However, this function, I cannot say it's continuous everywhere. It has a discontinuity that it's not removable. Where? At negative 2. I can't do anything about that. The vertical asymptote is not a removable discontinuity. The removable discontinuity is only at the hole, where both limits approach 1. So if I put this 1 in here, I fill in this gap. But I could never make this function continuous because of this. Continuous everywhere. I made it continuous at negative 1 by creating a new function. However, both functions are not continuous at negative 2. But this one is continuous at negative 1. This one is not continuous at negative 1 and not continuous at negative 2. Any questions? So I'm going to write continuous at x equals negative 1, not at x equals negative 2, where it has a vertical asymptote. Is this clear? Do you understand the mechanism of removing a removable discontinuity? I just have to create a new function and create that point that is missing from the previous function. Perfect. Anything else?
6.
Number 6, very good. 7, 6. Perfect. You will never hurt my feelings if you prefer a different method than mine. Please. I'm happy with you knowing the material no matter which method you use. But please summarize the information of this somehow before you attempt the graph. I recommend these tables because we're going to use them in the next chapters. Okay, when we graph, we're going to put everything together. You'll see how the mechanism works, and it will be extremely easy to understand. Some functions will not be very easy to graph. So I'm copying all this information directly in a table. So I see x approaches -2 from the left, infinity. So there is a -2 from the left, infinity. Done. Approaches -2 from the right, -infinity. Done. To me, this is going to be x equals -2, vertical asymptote. Okay. Limit of f of x as x approaches 0 from either side is infinity. Here's 0, 0 from either side is infinity. I'm going to call this x equals 0 also a VA. Limit as x approaches 3 from the right is 4. 3 from the right is 4. 3 from the left is 2. And f of 3 is 1. So now I have all the information very clearly in my table. So then I attempt the graph. I will graph x equals -2. This is an overkill, there is no need. X equals 0 and x equals -2. These are vertical asymptotes. I will plot the point 3, 1. I don't care about anything on the left-hand side, so I'm just going to say this. That's my choice. Then in between -2 and 0, it's coming from -infinity going to +infinity. I decided to make it a continuous function. You don't have to. You can break it anywhere you want. On the right-hand side of 0, is coming from infinity and going to 2, 3. I'm sorry, 3, 2, I meant to say. 3, 2. So it's coming from +infinity to 3, 2. And then 4. And then I can do whatever I want. So this is the graph. All conditions are fulfilled. Infinity on the left-hand side of -2, -infinity on the right-hand side of -2, +infinity on the left-hand side of 0, +infinity on the right-hand side of 0, 2, 3, an open point, 2, 3, an open point, 3, 1, a full point, and 3, 4, an open point. Any questions? Does it make sense? Next question, anything else? Anything from the limit handout? Any questions from the limit handout? We have about 12 minutes left. If you don't have other questions, I will pick some. Which one? From the limit, from here, yes, of course. 5, let's look at 5. Let's graph a piecewise defined function. Very good pick. So I'm basically using 2 sessions for each test in the hope that everyone will do very, very well on all tests. So we are using basically 4 hours, right? 2 hours today to review and then 2 more hours for the test. So that's already 4 hours, right? And we have 3 more tests. So please keep that in mind, right? Okay. which means that we still have to cover the entire material. I know we have 3 chapters left, but it's still a lot of material, okay? So please hold on to your seats. Okay, so we have f of x equals x squared minus 1 for x less than 0, and the square root of x plus 1 for x greater than or equal to 0. And we're asked to graph and then explain all continuities, left-hand side, continuous from the left, from the right, removable or otherwise, or jump discontinuity, whatever, right? So it says just present all continuities or whatever happens to this function, present it. Okay, so remember with the piecewise defined function, I highly recommend this, but if you have other methods, I accept them gladly. I recommend writing negative infinity to 0 and 0 to infinity because you know what's next, you know what I'm going to do. I'm going to use a table of values of ordered pairs eventually, and I'm going to use these symbols that signify an open point and a full point. So you already know the drill. So I see all real numbers, nothing is missing, but that's not always the case, right? So I see negative infinity to infinity and definitely 0. And underneath 0, I will have these 2 symbols, and they are touching. So the same type of table I just used here, in which all these parentheses, right, or open points, in other words, undefined in this case because of the vertical asymptote. The same thing here, this is a point, but these are open points. When a bracket and parenthesis touch, there is no such thing. And 2 open points, and a full point in the middle, right? So everything ties in together. I cannot use this because I have this. Meaning this will be a full point and this will be an open point. If it happens that these 2 numbers are the same, it's just a full point, and I'm done. But we'll see, I don't know. The next step I recommend, if you would like to do this, if you want to use this method, then to the left-hand side, I will be using x squared minus 1, and to the right-hand side of 0, I will be using the square root of x plus 1. You can say, well, I don't need to do this, it's an overkill. I already have the functions right here. True. But what if they are arranged, just to trick us, in the opposite order? You may by mistake plug in the opposite one. So that's why I'm saying be very careful. Okay, so I know that this is a quadratic function, so I'm going to definitely plug in negative 1. When I plug in negative 1, I get
0.
perfect. When I plug in 0, I get inside the parenthesis, which signifies an open point potentially. Yes. So if you want, we can plug in another number, all with C, because I already know this graph. How do I know this graph? Okay, here is the graph of x squared. Where does x squared minus 1 go? So I know the graph of x squared. X squared minus 1 will be this. Good. Okay, what about the square of x? So I plug in 0, and I get 1. I would like to plug in 3 to get 2. Okay, so let's graph. Negative 1 is 0. At 0 is negative 1 with an open point. The graph again should have been this, but now it's down 1, and this is only the left-hand side of 0. That's it. Only the left-hand side of 0. On the right-hand side, and that's why intentionally I'm using a different color, I start at 0, 1, which is a full point, and at 3, I get 2. And here it is. How do I know that graph? Because I know I have the square root of x plus 1. It starts at 0 to the right. I cannot extend it to the left, like I cannot extend x squared minus 1 to the right. It's only carved in stone between negative infinity and 0. What can I say about this function? This function is continuous everywhere except at, but it's continuous from the right of 0 because the limit from the right and the function value are the same. It's a jump discontinuity. Does this function have a removable discontinuity? No, there is no removable discontinuity. And what would be the range? We know the domain, I already put it in the table, that's good enough. What is the range of this function? From
-1 to infinity.
-1 to infinity with a parenthesis at -1. So this is what I would write. Continuous everywhere except at x equals 0, where limit from the square root of x plus 1 as x approaches 0 from the right equals f of 0, which means continuous from the right. Range you already gave me, parenthesis -1 to infinity. No removable discontinuity. No removable discontinuity. You want to write jump discontinuity, that's good too. Jump discontinuity. And that fulfills everything, all the explanations. Does the function have a removable? No. What is a domain? Yes, we wrote that. Is the function, yes, not continuous. Determine continuous from the right or from the left? Yes, it's continuous from the right, not continuous from the left. Anything else? If you would like, you can, I can be here earlier for you if you'd like on Thursday. If you'd like to start early, I can be here earlier. Just let me know so I know, and I'll be here. Is anyone interested? You may have another class. You want to take in the testing center, you are entitled to if you want to. But if you want, you can do it here. It's up to you. But it depends on you. I don't want to get in trouble with them.
No, yeah, because I can take it during the time frame, right?
You can take it the entire day, but not past 7 p.m.
Right.
Because when everyone finishes, I would like you to finish, but it's up to you.
Could I still come early if I took it at 4 there? Or at 5 there?
You don't have to come here because